Hello guys, in this video we'll be discussing about the shape of the ship, more specifically why ships look like this. No, it's not a very good drawing, but you kind of get what I mean. It's like this curve, right? It's the front bit of the ship is very curved, and you've probably heard some people say, oh, design something streamlined, which has been given to our vocabulary as something very optimal and like the most efficient way of doing so. So what are the connections of these things? What does streamline even mean? And like, why don't we build rectangular ships? What's the point of not building these ships? Well, first, let's discuss about the definition of streamline. Imagine you've got a field, right? This is your field, and you have some points here. You record a few points, right? And then you mark the velocity of each point. Let's say at this point, the velocity of the fluid is like this. So at this point, fluid is moving this direction this much, and at this point, the fluid is moving this direction this much, right? Then we draw a line that connects all these velocities perfectly, beautifully, right? And we call this line the streamline. In other words, streamlines are the lines that are tangential to all the velocities at a certain point. Now, consider a particle A, right? A at this point, this particle, if you just leave it in a steady flow, how will this particle travel? Well, the particle would travel following the velocities of each point, because we define this as how the particle here will move at a certain point. So then it will just keep on following the velocities. And oh, what does this look like? Well, this looks like the streamline. And this is also happens to be the path line. We call this the path line because this is the path of this one particle. The path line equals a streamline in a steady flow. And then we collect a bunch of particles together, right? There will be other particles in this fluid that does the same. And then if we connect these particles together, right, it will also look like this. Why? Because each particles are at given points at certain time. We can kind of know it from the path line. If you analyze each path line, you would know that streamline, path line, and what do you call this line that connects all the particles? We call this the streak line. These are all the same. Yes, these are all the same. So if you keep on shooting these particles from this point, they will eventually reach all these points. And we call that streak line, streamline, path line. They're all the same. Now, if you build if you have an object that goes through a flow, it will make some form of new streamline. How do you calculate this streamline? Well, these can be calculated by analyzing some properties, like solving the Euler's equation, solving the, what do you call that? I don't know, Navier-Stokes equation. By solving those equations and analyzing each point, we can kind of know the streamline of this whole path. Now, I will not include the details of calculating the streamlines, that will take way too long. But still, I think this is sufficient. And when an object, when these objects look like these, the streamlines would form like in a very odd kind of way, right? In fact, there will be a very low pressure zone over here, and all the streamlines would get messed up. You could actually create turbulences around here. At that point, streamlines make no sense. So in this case, the streamlines are all messed up and the water would have to travel way too much, and this is clearly less efficient than these kind of shapes where water can just go without much perturbance from this particle. Now, so why is this a better shape than this? Well, think about this. This point, think about water particle that travels in this direction. Well, in case of ship, the shape would travel to the left, but we can consider it as the water particle traveling to the right. Once it reaches this point, the water particle would stop and give all the momentum to this ship. And because of conservation of momentum, this ship would be slightly pushed to the back. Right? And however, when you make the shape generally streamlined, the water particle would not just stop, but actually carry on moving, which is one benefit of having so. Second benefit of having these cool kind of shapes instead of rectangular is that, remember all the water particles stop at this point? So if you think about it, there will be significant amount of water particle here versus there will be like only a few water particles at the back. All right, so there is this much pressure difference, and if there's a pressure difference, then because the nature wants to stabilize all the pressure, they want to make it all equal, the ship will actually be pushed back because of these accumulate of pressure. Whereas if the ship looks like this, then there will be a relatively similar amount. Well, it's not at all similar, but more similar than this. And therefore, less pressure difference, so less force moving to the back. Now note that having low pressure here isn't necessarily a bad thing, but generally, if there's this much difference, well, your ship will not be moving forward very well. Third one, kind of links to this, is that if there's this amount of pressure accumulated, think of the 3D shape. So that will be our boat, and this is our pressure point. If there's a very high pressure here, it will create a lot of wave. Yes? And because of conservation of energy, if you made some wave here with certain amount of energy, that means that this ship must have lost its energy. All the energy was used to create this wave, so this ship now has less energy. These kind of ships, the second type of ships, would have a smaller pressure point, and therefore there will be less of a wave. fourth benefit of having these kind of beautiful thing is actually the boundary layer. Now, this is a concept that around an object, the velocity of the fluid is 0. And then, so the velocity here would be 0 plus something. This would be 0 plus something bigger, and so on. So there will be a little bit of area where the velocities are smaller, right? It's 0 here, and outside velocity is, let's say, this much. Then these area, while the velocity here is catching up, would have a slower velocity. So then, if you mark the boundary layer of these two shapes, one's boundary layer would look like that, kind of. So, I mean, okay, it's not all this dramatic, but I'm just showing you. I'm just exaggerating a little bit. And this boundary layer would look like this. And as you see, there is significantly more boundary layer here. And what happens here is that there is a viscous drag from all these boundary layer with slow moving fluid. There's a viscous drag from Newtonian fluids that just drags it just wants to keep the speed. And also, again, to the idea of the pressure difference, there's slow moving, like little pressure objects here. There's high pressure, moves it back. So these are basically primary reasons why ships look like that. And also sometimes you would actually find some ships that look like this, right? If you see like big container bulks, they will almost necessarily have this kind of structure here. Now, what does this structure do? Well, you remember that ships here create waves. Well, if the ship looks like this, the pressure would be accumulated in 2 points, not one, which is this point here and this point here. Therefore, the wave would be created like that, and at this point, wave is created like this. Now, you should know from basic knowledge of physics that if this wave and this wave meets, they kind of annihilates. Now, this part here, called the bulbous ball, because it's bulbous, can control the pressure point at the front and allows you to create arbitrarily where the wave is formed from. So whereas without this, let's say it just looks like this, the wave would be formed from here, and the shoulder wave could be somewhere like here, let's say. Let's be dramatic, and that's the shoulder wave, right? The resultant wave would actually look like this, and you would create an even bigger wave, which creates, which spends more energy and therefore more resistance. If you have a bulbous bow here, remember, with the bulbous bow, you would create your wave here, and maybe the shoulder wave comes from here, right? Then the resultant wave would actually look like that. So it's a much smaller wave than this wave, and that's why bulbous bow can remove the resistance by quite a lot. And bulk containers would almost necessarily have this.